Hey everyone, and welcome to the AI Research Roundup. I'm Alex, your host, and today we're diving into some fascinating AI research. We'll be looking at a paper titled HealthGPT, a Medical Large Vision Language Model for Unifying Comprehension and Generation via Heterogeneous Knowledge Adaptation. So, what these researchers have done is present HealthGPT. It's a powerful medical AI model designed to both understand medical visuals, think X-rays or scans, and also generate related content. It aims to do this within a single unified system, using a novel technique they call Heterogeneous low-rank adaptation. They also created a special dataset just for training it. Okay, so Figure 1 here really gives a great overview of what HealthGPT can do. You can see at the top it shows 7 different comprehension tasks, like analyzing X-rays, CT scans, microscopy images, and answering questions about them. And then the bottom half shows 5 generation tasks, things like converting a CT scan to an MRI representation, reconstructing images, improving resolution, and even generating a chest X-ray from a text report. The figure also includes charts showing HealthGPT's performance, demonstrating it generally outperforms other models on both types of tasks. It really showcases that unified capability we talked about. Building on that idea of unifying tasks, Figure 2 here really illustrates why that's tricky. These plots basically show a performance trade-off. In plot, when you add more generation data, the model gets worse at comprehension. See the teal line dipping? And then plot shows the reverse. Adding more comprehension data makes generation performance drop. That's the red line. It highlights this inherent conflict between understanding the big picture and generating fine details, which is exactly the problem HealthGPT aims to fix with its methods. Okay, so Figure 3 gives us a look under the hood at the HealthGPT architecture itself, showing how it actually tackles that conflict we saw in Figure 2. You can see it takes in medical images and text instructions. The key thing here is this HLoRa component in the middle. It has these separate modules, kind of like plugins, specifically for comprehension and generation. It uses a router to direct the information, deciding which plugin and which visual features are needed for the specific task, whether it's understanding an image or creating one. This separation is really how it avoids that performance trade-off. So, to train this architecture we just looked at, the researchers actually curated a specific dataset called VL Health. Figure 4 here gives us a breakdown of that. Part A shows the different types of medical data and tasks included. You can see various imaging types like CORT, MRI, X-ray again, plus tasks like reconstruction and text-to-image generation. And then Part B shows the scale. They gathered a pretty large amount of data, around 765,000 samples for comprehension tasks, and about 783,000 for generation. Okay, so after training on that VL Health dataset we just discussed, Table 1 here shows us the results, specifically focusing on medical comprehension tasks. It compares HealthGPT, both the M3 and L14 versions, against other models, some that only do comprehension, and others that try to do both comprehension and generation. If you look at the average scores on the far right, HealthGPT M3 gets 61.3, and L14 gets 66.4, which is way better than other unified models like Unified IO2 at 33.8, and even beats strong comprehension-only models. This really shows that their approach works, unifying tasks without losing that crucial comprehension ability. So, we just saw how well HealthGPT does on understanding medical images in Table 1. But what about the generation side? Well, Table 2 here shifts focus to exactly that, specifically looking at medical image modality conversion tasks, like transforming a CT scan image into an MRI representation, or the other way around, for both brain and pelvis scans. It compares HealthGPT M3 and L14 against several other models using standard image quality metrics. You can see HealthGPT generally outperforms the others across these different conversion tasks. For instance, on CT to MRI for the brain. HealthGPT M3 achieves an SSIM score of 79.38, beating methods like PICS, 2PICS pretty clearly. This really backs up the claim that it excels at generation 2, not just comprehension. Now Figure 6 digs a bit deeper into how HealthGPT manages both understanding and creating images so well, specifically looking at the different types of visual features it uses. Part A here shows the training loss. The red line represents using more abstract features, sort of the big picture information, while the orange line uses more concrete, detailed features. You can see the red line generally leads to lower loss for comprehension tasks, while the orange line gets lower loss for generation tasks. And then, Part B really confirms this with the performance bars. Abstract features, the red bar, perform better for comprehension, while concrete features, the orange bar, do better for generation. So, this supports their strategy of using different levels of visual detail, depending on whether the model needs to understand or create an image. Okay, so seeing how HealthGPT uses those different features really brings it all together, doesn't it? This work is pretty exciting because it successfully unifies both understanding and generating medical images within one model, which is a big step forward for AI in medicine. It really shows the power of adapting these large models specifically for healthcare challenges. Well, that's all the time we have for today. Thanks so much for tuning in to the AI Research Roundup. I'm your host, Alex.